Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. Now, much of the inspiration for category theory comes from topology. So it's only fitting that in this video, I'm going to give you several of the motivational examples of functors that arose in topology and really kicked off the whole game. So the first thing that I want to do is to give you the category that we want to work with, okay? So it's not quite the category of topological spaces, it's something called the homotopic category, which is a lot more interesting. And that's something that the topologists study quite a lot, okay? So firstly, I want to define the notion of a pointed space, okay, which is just something slightly richer than a topological space. It consists of a pair, big X and little x, okay? The big X here is just some topological space, and also the little x is going to be just some point inside big X. Okay. Now we want to have a notion of morphisms between these two things, okay, homs between them. So what's a continuous map from this pointed space x, x0 to this pointed space y, y0, okay? So firstly, it's a continuous map from the topological space from x to y here, g from x to y, continuous map. And how does it respect the extra points that you have in these two pairs, okay? It has to send the point x0 inside big X to the point y0 inside big Y. Okay, so that's what we have. Okay, so let's look at a little example that's going to be important and will also motivate the next definition that I want to come to. Okay, so here we have a pointed space. It consists of the closed interval from 0 to 1. Okay, and we're going to add a point to that. So that's the topological space. We're going to add a point to that. That's going to be the 0. Here's another pointed space. It's going to consist of the plane, or R2, two-dimensional Euclidean space, and then we're going to look at the 0 is the point that we fixed inside it, okay? So what's an example of a continuous map? So this represents an example of continuous map. You just map this interval here homeomorphically onto this interval here, okay? That's all you do. And then we'll call that G0, okay? So let's look at another example. We can also map this here to a line segment like this, where the 0 gets mapped to the 0 vector here, and this line segment gets mapped to this line segment. Okay, so let's call it G1. Now in this example, we can actually put similar sort of continuous maps in between. So for example, I can put something out in the middle like that and call it G half. Okay, so maybe I only want to make it actually length 1. Let's just change it so it's the same length. So it should go out like that. Okay. And in fact, you can do more. You can actually interpolate all the way in between continuously. So you can start from this G0 and then just move out little by little all the way up to G half, and then keep going all the way up to G1. And you can interpolate continuously, not just discrete like I've drawn it here. So you can smoothly go from this map all the way to this map here. And when we're in that situation, we want to say that these two maps are homotopic. Okay, so let's give the proper definition for what that means, okay? So suppose you have two continuous maps between pointed spaces x, x0 and y, y0. Suppose those continuous maps are G0 and G1 like we've got here, okay? When are they homotopic, okay? So we're going to use the following definition here. It involves kind of lifting this continuous map to a continuous map from not just x to y, okay, they give you G0 and G1 essentially, but from x cross the line segment 0, 1 to y, okay? So you want a continuous map from x cross 0, 1 to y, such that what happens? Okay, so firstly, if we just restrict this map where the second coordinate is 0, so g of x comma 0, this just recovers for you the first map G0, so that's just G0 of x. If we restrict the second coordinate just to 1, that gives you the second map, gx1 equals g1 of x, okay? So that's the first thing that you want, okay? So to speak, if you restrict to either end of this interval, you'll get the two continuous maps, G0 and G1. And basically, we've interpolated between them by smoothly defining this G also for all the values of inside here, the second variable between 0 and 1. So the other thing is that it should respect the point. So you want to make sure that it doesn't matter what your second variable is, t, no matter what this is, it takes the point x0 to y. So g of x0 comma t is equal to y0. And that's the notion of homotopy, or when these two are homotopic to each other. Okay? So in this case, we'll call G a homotopy. And this actually gives you an equivalence relation. It's quite easy that, for example, to test symmetry, if you can build a homotopy from G0 to 1, so you basically continuously go from G0 to 1, you can also sort of just reverse the way you traverse from 0 to 1 and go backwards from 1 to 0 and just slide from G1 to G0 to give a homotopy the other way. Okay, so it's quite easy to see that actually being homotopic is an equivalence relation. Okay, so we'll use this symbol here to denote that. Also, just as we've done here, okay, we can fix the second variable t, and then when we fix the second variable and make the first variable vary over all of x, of course we're restricting this to this function g by restricting what the second variable is, then you'll just essentially get a function from x to y, and that's a continuous function. And because of this condition b here, actually it's a continuous map of these pointed spaces. Okay, so you'll get this g subscript t. Okay, so basically another way to think of this is that you kind of have a family of continuous maps of pairs gt going from g0 to g1, and t starts at 0, it goes up to 1, and basically you interpolate between them, and this is smoothly dependent on t. And what is smoothly dependent or continuously dependent on t, and what is continuously dependent on t mean? It just means that this g, when you look at this as a map from the cross product here to y, that's continuous. Okay, so that's the notion of homotopy, and now we can define the homotopy category. Okay, that's easy enough. Okay, so firstly, a homotopy category of pointed spaces. Okay, it's going to be denoted this, we'll denote it in this video at least as underline of h top. Okay, so we need objects, we need homs, and we need the composition of homs. Okay, so what are the objects? The objects here are just pointed spaces. And now, in this case here, the homs aren't just special types of functions. Okay. They're going to be given by continuous maps of these pointed spaces, but now we're going to look at equivalence classes of them. Okay, so this is continuous maps modulo this homotopy equivalence relation. Okay, so homotopy equivalence classes of continuous maps give you the homs. Okay, so since we have this equivalence relation, of course you can put equivalence relations on these hom sets of continuous maps, and that gives you indeed a set. Okay. And now what we want to do is we want to have composition. And the point is that composition of continuous maps will actually induce compositions on these new hom sets. Okay, so these sets of equivalence classes. Okay, so there's something to prove to check that you do indeed get a well-defined composition here. So the basic idea is, suppose you have two continuous maps, okay, and you want to compose one with another. Okay, so you have two continuous maps. Of course, if you change one of the maps to something which is homotopic, you want to show that the composition is homotopic to the original. Okay, so if you change either of those maps which are composed to something that's homotopic, then the composite remains homotopic to the original one. So you don't change the homotopy equivalence class of the composite. Okay, so you can check that, it's not so difficult, and that gives you the homotopy category of pointed spaces. Okay, so now that we've got the category of interest, we want to look at some of the functors that occurs. Okay, and the first thing we want to do is the following. So we're going to look at what's called the fundamental group, which is extremely important. Now, one functor that we always have is, of course, the hom functor, and the hom functor you can get by picking any object inside your category. Okay, so here what we're going to do is we're going to pick inside this category h top the following object. It's going to be S1, which is just a circle here, and then PT just represents any point. Okay, because of the symmetry of the circle, it doesn't really matter which point you pick. Okay, so it's just S1 point. Okay, and the idea of this functor here, the fundamental group, is you want to probe a pointed space or topological space by using circles. Okay, that's the idea of the fundamental group. You want to probe it by using circles. So what is this hom functor? You just look at all the homs from this pointed space S1 point to your pointed space. Okay, so this is going to be a set of homs. Okay, it's the set of all homotopy equivalence classes of continuous maps of pairs. So this is a functor where if you put in a pair, you get out this set of homs. Okay, so that's all very well and good, and that's nice, and that's one way to probe a topological space or pointed space with this circle. Okay, but what we're going to do to get more information out of that is the following. We're going to actually lift this from a functor from this homotopic category to sets to a functor pi1 from the homotopic category to groups. Okay, that's the idea. Okay, so this is the fundamental group, pi1. So what does that really mean? Okay, so this is what I mean by lift. Okay, so suppose you have some pair x0, and we want to define the object, which will be a group pi1 xx0. Okay, so certainly we can do this construction here. It'll be just the homs in the homotopic category from S1 point to xx0, and that's a set. Okay, so we'll have a set. So this is what you get if you use this functor up here, just the usual hom functor. But the thing is now, this set, what we're going to do is we're going to put a group structure on it. We're going to put group multiplication on this set to make it into a group. And then, of course, this is a functor. So, of course, if you have a hom between pointed spaces, so a continuous map between pointed spaces, that will induce a map on sets. And we want to check that that's also a map on groups, this group structure on here. Okay, so let me show you how that works. Okay, so let's suppose we have an element, or say two elements inside here that we want to multiply together. Okay, so how do we represent them? Okay, so what is an element inside here? It's just a homotopy equivalence class of continuous maps from here to here. So let's just pick a continuous map from S1 point to xx0. Here's my x, and here's my xx0, xx0. And one way to think of a continuous map from here to here, okay, of pointed spaces is firstly, you have to map the point to the point, and then you can trace around the circle like this. So to map over there, it's basically just a trajectory that starts at x0 inside x and ends back at x0. So maybe it's something like this. Okay, it's a trajectory like that. That's gamma 1. Okay, so that gives you one element inside here, and you want to look at homotopy equivalence classes of them. Let's suppose we have another element, maybe this one here. Okay, so now we want to have an element that's inside here, which corresponds to the composite of these two, the group product of these two. So we need basically a trajectory from x0 to x0, which somehow combines the data of these two direct trajectories. Okay, and there's an obvious one to pick. Okay, what you do is you move twice as fast along the gamma 1, and then afterwards you follow that up by gamma 2. Okay, and that gives you a trajectory that starts from x0 and ends back at x0 and incorporates both the data of gamma 1 and gamma 2. Okay, easy. And that's going to be the product of those two. Another way to think of it is as follows. Okay, what you can do is you can map this S1 and this point to this figure 8 here. Okay, so you map this point to here, and basically you pinch the opposite point back down to this point here, and then you get one loop going to from here to the opposite point. That becomes that one, and then as you complete the bottom half here, you finish the second loop. Okay, so that's a continuous map that you can see. And then the product of gamma 1 and gamma 2 is now you have two circles, okay, and there's a distinguished point for both of them. You apply gamma 1 to this top circle, and then gamma 2 to this top circle, so that gives you the map here, and the composite is the map which gives you the product. Okay, so this is another way of defining the composite. Okay, and what's really nice is that this actually gives you a group on this this set here. Okay, and if we didn't look at homotopy equivalence classes, of course you can't do that. Okay, but if you do look at homotopy equivalence classes, you can. So let me just show you, for example, why that's the case. Okay, so for example, gamma 1 is like this. Okay, what is the identity? Okay, so I guess there's a natural choice for what is the identity in this group. Okay, so it should be a fairly distinguished continuous map from this pair to here. Okay, so there's only one choice. This point has to go to x0, and where does the rest of the circle go? Well, the only canonical choice is you send all of S1 to this x0. Okay, so that's a constant map from S1 to x0. That's going to be the identity. So let's see how that occurs. So suppose gamma 2 now is this constant map. So that means that now what is the composite of gamma 1? with this constant map. So basically you go around this loop, okay, twice as fast, and then you just stay with the constant loop here for the rest of the time. Okay, so of course that's the same as just this loop here, because now you've rushed around this twice as fast and then you halted here. But the point is that these two maps are actually homotopic to each other. Okay, so they're equal inside this hom set here of homotopy equivalence classes of continuous maps. Because what you can do is you can, if you start by going twice as fast, you can go slower and slower until eventually you spend no time waiting here and you end back at your original gamma 1. So that's the homotopy, the shift from one to the other. Okay. So other things that you need to check, for example, is the existence of an inverse. Okay, so what's the inverse of going from gamma 1 around like that? Well, I hope you can guess what it is. It's got to be something that just involves this gamma 1. And what you do is you just trace it around this backwards. Okay. So what you can do is the composite is going to be you go twice as fast around this and then go twice as around fast, but in the reverse direction to come back to where you started. And what you can do is that since now the only thing you have to fix is the beginning and the end, you don't need to fix the midpoint, which was back over here. So you can, rather than going all the way, to show that composed path going around like this and coming back is homotopic to the constant here, so basically gives you the identity, what you can do is you can shorten the length of this. So rather than going all the way to the end, you can go almost to the end and then come back. And then you can keep shortening this until you just get the constant path at x0 or the constant loop at x0, and that's the identity. And that just shows you that tracing around gamma 1 in the opposite direction is indeed the inverse of gamma 1 in this pi1x. We finally arrive at the following theorem that I hope you can guess. Okay, so this object here, pi1x x0, it was defined as a set and we put some multiplication on it. That in fact is a group and it's called the fundamental group. Furthermore, okay, this assignment where you put in this pointed space and you spit out this group, remember this also comes from a Hom functor, so this induces a map on the underlying sets of these groups. That actual map of sets is actually a group homomorphism, so we now get a functor pi1 from the homotopic category to the category of groups. Okay, so this is the theorem that gives us one of the most important functors in topology. Okay, so just some remarks about this group here. Okay, of course you're looking at loops which start and end at x0. They're the elements inside this set. Okay, so of course you can't get out of the path component of x which contains x0. So the only information that you pick up about this pair is just that path component which contains this little point, this x0 here. The other thing is, well, how dependent is this pi1x x0 on that point? Well, it turns out that if you move that x0 in that path component, you'll just replace this with an isomorphic group. So to a certain extent, it doesn't really change it that much. And that's probably what you would expect. Okay, so let's look at a little example which shows you a simple computation of a fundamental group or homotopic group. Okay, so the thing we're going to look at is the closed unit ball B n bar inside n-dimensional Euclidean space. That's going to be our x. Okay, so here's the picture in the case n equals 2 here. And in this case, it's a bit easy to see what's going on, because in this case, this as a pointed space inside this homotopic category is very, very trivial. Okay, it's actually isomorphic in this homotopic category to the point. Okay, so to show that they are isomorphic, what you have to do is you have to show that there are inverse isomorphisms between them. So this point, suppose you pick the point to be just the center of this closed unit ball. Okay, so you can have the point. That of course just includes inside here. And of course, how can you map back the other way? Well, there's only one way to map the other way. That is, you have to send all of this beta bar down to that point. Okay, and I claim that they're homotopic to each other. Okay, so how is that? So basically, I want a family of maps from B2 bar back into itself until suddenly it deforms from the identity map, okay, down to the map to the point. Okay, so how do I do that? Well, of course, this B2 bar, okay, I can map this to the ball of radius t. okay, isomorphically to the ball of radius 2 just by shrinking everything, scaling everything down, okay? So you let t vary from t equals 1, so that's the identity, down to t equals 0, okay? That gives you a continuous map, and that gives you the homotopy, that gives you the isomorphism in the homotopic category between this and this very trivial pointed space point, comma point. Okay, so that tells you that since this is a functor from here to here, and so isomorphic objects get sent to isomorphic objects, that means that pi1 of this pair here is isomorphic to pi1 of the pair point, comma point. Okay, so what is pi1 of this? Well, what you have to do is you have to look at homotopy equivalence classes of the circle, continuous maps of the circle mapping to the point. Well, there's only one map, continuous map from the circle to the point. In fact, there's only one map from the circle to the point, and that's going to be the constant map to this point. So of course, this as a set is just 1, okay? So that tells you that this group here just has to be the trivial group, just 1. Okay, great. So that gives you one computation, but unfortunately, in some ways, it's not so interesting because this is a trivial group. Okay, so you can't. It seems like you can't get much information out of it. So the only way you can get really interesting information is if you have some non-trivial fundamental group. And unfortunately, computing the fundamental group is not easy. Okay, so let me give you a theorem which tells you what one of them is, and that's the simplest example. Okay, so remember, what you're trying to do when you look at the fundamental group is you're trying to understand a topological space by probing it using a circle, right? So S1. So we're going to look at the case of a circle, and the circle here, I'm going to imagine it to be inside the complex plane, the Argand diagram. So you're looking at the complex number Z with modulus equal to 1. So let's say, suppose this is this here, and you want the pointed space, so let's pick the point 1 here, okay? So that's what you have, S1, 1, and we want to look at pi1 of that. So if this is trivial, of course, you'd expect that since you're probing this with circles, then this is not an interesting notion. But the point is that this is actually non-trivial, okay? And how non-trivial is it? It's actually isomorphic to Z, and I can tell you what that isomorphism is, okay? So how is Z isomorphic to this? Okay, so that means I have to give you a map from here to here, which is a bijection. So where does the integer n go to? The integer n has to go to some element of this, remember, which is a homotopy equivalence class of loops in S1, which start and end at this point. And basically, what n goes to is it's the loop which goes around n times. Okay, that's what it is. So in other words, if you think of it in terms of this S1 being this unit circle inside C, then it sends the complex number Z with modulus 1 to the complex number Z to the n. Okay, and that wraps around n times. For negative values, it wraps around n times, but in the opposite direction. And if you think about it, of course, you don't expect going around n times to be homotopically trivial, so to be homotopic to the constant map of the point, which is the identity, okay? Okay, so you would think that that looks like an isomorphism, and that indeed is. But it's actually quite difficult to prove that theorem. Okay, so what I want to do now is I want to show you how this notion of a fundamental group gets used in topology, and in particular, how it motivates a lot of the ideas in category theory. Okay, so one of the things that we saw in the previous video is firstly that in the notion of a category, you can always talk about not just isomorphisms between objects, but left invertibility. And the other thing that we saw is that we can talk about functors, and functors preserve left invertibility because they preserve left inverses. So let's see how this notion arises in topology. And it arises in this little lemma here, for example, amongst many other things, okay? So basically, the notion of a left inverse in topology, in this homotopic category, corresponds to a weak retract, okay? So suppose you're in this situation of this picture here, okay? You have some point that's inside S1, and of course that's the boundary of the closed unit ball, or closed unit disk, B2 bar here, okay? And of course you have an inclusion of the circle into B2 bar, and hence of this pair, this pointed space to this pointed space here. Iota, that's my inclusion. And the point of this lemma, the claim here is that this inclusion map is not left invertible. So you can't find a map from here to here such that the composite is going to be the identity. Okay, and why is that true? Okay, so the key point is that once you have a functor, okay, which takes you from topology, okay, in fact this homotopic category, over to something like groups, okay, you can ask yourself the equivalent question with groups, and sometimes that's a lot easier to answer. So that's what we're going to do, okay? Suppose this were left invertible. Let's just apply this pi1 to it and see what we get. Then we get a map from pi1 S1 point, which I said via this theorem is isomorphic to Z, to pi1 B2 bar point. Now remember, this is homotopically trivial, like we saw in the example, so this fundamental group here is just 1. So here in groups, you have a map from Z to 1, which has to be, of course, the constant map to 1 here. Okay? And the key point is that in groups, it's very easy to see now that this is not left invertible. Okay? You can't have a map from 1 to here such that the composite going from here to here to here is the identity on this. In fact, the only group homomorphism from 1 to here has to take identity to identity, so 1 gets then to the 0. So when you compose a map from here to here, or any map from here to here, it has to be the map which sends Z, all of Z to 0, so it can't be the identity. That shows that this map here, okay, is not left invertible, and hence the original map, since we just applied a functor to it, the original map inside the homotopy category is also not left invertible. Okay, so great, we've shown that this is not left invertible. Does that give us any interesting information about the topology of what's going on? And in fact, we're going to show that this actually gives us what's called Brouwer's fixed point theorem. And this is a beautiful theorem, and the result really hinges on this little categorical fact here. Okay, that's the key thing, once you've set up the theory of this functor and fundamental groups. Okay, so let's see how that works. Okay, so what is Brouwer's fixed point theorem? Okay, so it gives you the existence of a fixed point, and in what situation. Suppose you've got a continuous map from this closed disk to the closed disks, B2 bar to B2 bar. That's your continuous map F. Okay, then immediately we know it has a fixed point. Okay, so why is that true? Okay, so this is rather interesting fact. Okay, it's certainly not obvious. Okay, and the way we're going to do it is as follows. Okay, what we're going to do is we're going to suppose this is false, and we're going to derive a contradiction to this lemma here. In other words, we're going to find a left inverse to this inclusion. Okay, we're going to actually define an actual map which is going to be left inverse to this. Okay, so the left inverse of this inclusion, this will be a map G, has to go from here, this closed unit disk, B2 bar, comma point, to the boundary circle S1 point. Okay, how do we define it? Okay, we define it as follows. Okay, so suppose now that there's no fixed point. Okay, so here's our disk. Okay, so we want to find a map from B2 bar, so let's pick an element inside there, X, and we want to map it to the boundary circle in such a way that it's a left inverse to the inclusion map. Okay, that's the object. Okay, and we know that f of x, we have a continuous map from the closed unit disk back to itself, so f of x is some point in here, and we assume that there are no fixed points, so f of x and x are different actually. Okay, so once they're different, what can you do? Well, you can draw the directed line segment from f of x to x, and then you can keep going until you hit the boundary. Okay, and there's a unique point there. Okay, so you start from f of x, and since that's different from x, you have that directed line segment. You continue along that line segment until you hit the boundary in a unique point, and that point is going to be your g of x. Okay, so I claim firstly that this is a continuous map. Okay, so if you move x continuously, okay, what happens? Well, this will move continuously, then f of x will move continuously as well. So the ray will also move continuously as well, and hence where this ray intersects the boundary circle, that's going to move continuously as well. Okay, so we see that g is a continuous function of x. Okay, so does it map the point to the point? Okay, well, in fact, I'm going to show you even more. Let's show that this is actually a left inverse to the inclusion. Okay, so you have the inclusion from here to here. So let's pick a point on S1. You include it in here and see that when you apply this g to it, you get back to the original point. So suppose the x now here was on the boundary, say here. Okay, then what do? Then what you do is you look at f of x, which might be a point like this. You draw the line segment, directed line segment from f of x to this x on the boundary, and you see where that intersects the boundary. Well, of course, that's just x. Okay, so in that case, if x is already on the boundary, then g of x is equal to x. And in particular, for this point on the boundary here, it sends this point to this point. Okay, and hence we see here from this picture immediately that we've constructed a left inverse to the inclusion of this circle into the closed disk, which contradicts this lemma. And that contradiction shows you that indeed any continuous map from the closed unit disk to the closed unit disk has a fixed point. Okay, so this is a lovely theorem, and this proof depends on two things. Firstly, setting up this theory of this functor. Okay, and once you have that functor set up, okay, you use these categorical notions of left invertibility to finish off the proof. Okay, so to end this video, I want to talk about other functors in topology, because this is far from the only one. This is a very important one, but there are lots of others which are extremely important as well. So this functor here involved probing topological spaces using a circle. And you can ask, well, what happens if you try to probe a topological space with n-dimensional spheres? So here we can look at the Hom functor from Sn point to some variable pair, okay, pointed space. Of course, that's some functor from the homotopy category to sets, and in this case here we can lift it to not only just the category of groups, but actually to the category of abelian groups in the case when n is greater than or equal to 2. Okay, and that gives you the nth homotopy group or fundamental group. Okay, and that's very, very important in topology. Another thing which is very interesting is K-theory. If you have X as a compact Hausdorff space now, what you can do is you can form an abelian group K of X, and what that is, it's the Grothendieck group of vector bundles. So if you don't know what a vector bundle is, you can look at my video on vector bundles, and I also have a video on what the Grothendieck group is there. Okay, so this is a way that you can construct an abelian group given a compact Hausdorff space. And this assignment, for each object you get some abelian group. You can also lift it so that if you have continuous maps of these compact Hausdorff spaces, you get a group homomorphism on the K's as well, these K groups. And that gives you a functor, a K functor, from the category of compact Hausdorff spaces to abelian groups. And the last example I want to talk about are the homology functors. They're very important. So for each natural number I, they have homology functors from the category of topological spaces to abelian groups. And similarly, you have cohomology functors from topological spaces to abelian groups. What's interesting about the cohomology functors actually is that you can take the direct sum of them for all natural numbers I, and that will give you a ring, in fact. Okay, so you can put a ring structure on that, and that gives you a functor from topological spaces to the category of rings. I hope you enjoyed this adventure in pure mathematics.